Thank you very much, Ebrahim, for the invitation and also for the kind introduction. I want to say also hello to online friends. John Sipe is there. So hi, John. I know that you are in Europe. So and when Ebrahim asked me to give this talk, I said, well, I'm looking to different regimes working with electrons and working with light, working with photons. And as any of you like physicists, I have interest in fundamental understanding of the nature. So the talk that I prepared is a peanut butter talk. So it's a little bit of everything, just having a smooth and nice story and sharing with you guys. James. So, please interrupt me any places that you have questions. There are a lot of details which I'm escaping them. So I'm not telling you the details. I will tell you only the big picture and what we are going to do. So essentially, as I said, I'm dealing with photons and also with electrons. So I categorized in two different languages, which is photons and massive particles. And indeed, when I work with photons, I'm dealing with Maxwell equations, and I like the quotient form because it's a relativistic one. Or some people, they say that you would like to have more maths, a complicated one, not for undergraduate level. So, and on the other side, of course, we deal with the Dirac equation. So usually I use the word of wave function for photon. Well, I'm very well aware of the situation that photons electric field is not a solution to the Schrodinger equation. I use it with the way and the fact that, well, if you introduce a Riemann-Silberstein vector, which is if you introduce the electric field and magnetic field to be the real and imaginary part of a vector, which are called F, then you can simply write the Maxwell equation in this way. So for colleagues that they're online, so I can write it in this way, okay? Fantastic. So with this way, I know that, well, I can treat photons, although is a massless particle, I can treat it like a solution to kind of the equation. Of course, the spinors that I have it here is a spin one spinors, and transversality will take the spin 0. So fantastic. So I'm using this word as wave function for the photons based on this fact. Well, if you do the quantization, if you do, let's say, solve the Schrodinger equation or solve the Dirac equation or partial wave equation, in any case, for massive or massless particle, what you will end up that the wave function essentially for photons or for the electron can be labeled by many different degrees of freedom. And one of those degrees of freedom essentially is the energy that you work with. It can be spin degrees of freedom or polarization, let's say, in a naive way for photon. You can work also with the statistics. So you can deal what is happening with the statistic of those particles. They are Poissonian, sub-Poissonian, or super Poissonian distribution. Or you can also work with the spatial distribution of them. So essentially what's going on with the let's say along in the transverse plane to the propagation direction, what is happening with the P and L degrees of freedom. And usually that depends really on the person. So for example, you can solve in 11 different coordinates. You have many way of doing the quantization. But since our optics, or let's call it, our optics, even in electron microscope, they are cylindrical symmetry. Usually we do this quantization in the terms of cylindrical coordinate. And one of the best solutions that we do have is Laguerre-Gaussian modes, which I'm sure that most of you heard about these modes. And when we do that, the quantization happens with L, the quantization happens with P, which they're associated to azimuthal degrees of freedom, phi, and also radial one. So the radial was forgotten by people. They've forgotten about the radial degrees of freedom until 2012, which with one of my supervisors, Enrico, we looked into the quantum property of that, and we show, yes, this is also a good quantum number. And when I moved to Canada, in Bob's team, we performed the first experiment and showing to the people, well, you can really label the single photon with a quantum with the radial degrees of freedom. And this is one of the examples that I like and show to people, which is, this is an example of the structure, photon of structured light. So essentially what you deal with is not look like a Gaussian, so which is a Gaussian profile, and is not look like a uniform polarization distribution, which is everywhere in the transverse plane. You have a certain polarization degrees of freedom, but point by point, intensity, phase, and polarization is changing. And this is extremely rich in terms of mathematics and also in terms of topology, which I will try to convince you in a couple of slides. And just to understand and distinguish the difference between orbital momentum and also the polarization, the structural light, this is one of the examples. So you can create a beam which essentially has certain polarization degrees of freedom, which is CQIQC polarization, but having certain orbital momentum degrees of freedom. And this is the distribution that you are expecting, is a donut shape, which point by point you have CQIQC polarization. But what you can do, you can go with a coherent superposition of different CQIQC polarizations by different OM state. And then what you will see that everywhere you have a linear polarization, but this linear polarization is changing in the transverse plane. Well, this example, they call it vector vortex modes. And also you can go with very complicated situation. You can also control the radial degrees of freedom, phase, and also polarization. Then you will end up with this kind of, let's say, pizza-like pattern. You can go even with a more complicated structure. So I will call these structured photons if I deal with photons, and you can control them. Well, there are many different ways that they can control this, that they can generate these kind of modes. The one is a plasmonic structure, so you can have nanostructures, which essentially locally you can excite the different polarization states, and then you can create, for example, orbital momentum. This is one of the examples that the thickness it was about almost 80 nanometer size. So, and you can create OM beams, or you can create structured beams at a visible domain. You can go with the liquid crystal technology, which I am in favor of that one for the historical reasons, because I did my PhD in Naples, and there we had a very good liquid crystal technologies laboratory, a fabrication lab. And you can, for example, create a beam which upon propagation is accelerating in opposite directions. So these beams, they call it airy beams. So it looks like a projectile. When you propagate it, then you will see that the maximum loop of intensity is going on a certain projectile. Of course, it's not violating the rules. What you will see is look like a missile, which essentially the center of intensity is almost constant, but what is happening, more energy goes to the tail. As a consequence, the loop of intensity goes in a trajectory. You can create a beam which is really high topological charges. You can create a beam which has orbital momentum of, let's say, 400. And this is one of those examples. So they were able to create orbital momentum of 400, but they did a superposition or let's say interference with another beam just to count how many phase jump do we have in azimuthal direction. And what you will get, you will see those small points. And essentially, I counted and I ended up with 399. And one of my, of course, students say, well, Ebrahim, you could act more smarter. So just write a code that you will have the loops and you can count the maxima. Of course, he was right. So with this liquid crystal technology, you can do many interesting things. Of course, it's still structured light, but remember that also you can apply the technological aspect of this. So one was about creating a mirror that they call it magic mirror. Have you heard of these? How many people? No. Okay. Oh, of course, I find this. Yeah. So this is a very, very interesting device which goes to several millennia ago in East Asia, which was fabricated by Chinese and Japanese. And it was a mystery until Sir Michael Berry resolved the problem. So you had a mirror, you look at the mirror, well, you see your image. Of course, it was like this, as a concave mirror. And then when you shine the light on top of this and you go to the far field, what you see a hidden pattern, which is look like this, appearing on the reflection. And this hidden pattern was independent of the place of image. So you could just watch it, right? So it was not looking like an image that appears in a certain plane and disappears in other plane. So it was in volume. So that was a mystery for people for many years. They didn't, not many years, 1,000 years. And people, they didn't know really what is happening. But Sir Michael Berry, he resolved it in a very simple fashion. And he said that, well, this should be a transformation from a coordinate to another coordinate. And the energy should be conserved. And if you change the coordinate, is a basic calculus, you will deal with the Jacobian, right? And if you do the Jacobian within certain approximation, he found out that, well, the image that appears is essentially a Laplacian. Laplacian of the height changes. And this is extremely smooth modification on the back of the mirror. So essentially, if I want to tell you in a simple way, you have, if you want to create an image, you have to look at the Laplacian, and Laplacian is not going to look like a Fourier transform, which gives you really the sharp violation or sharp variations, but essentially is a very, very smooth variation. And if you craft this smooth variation on the back of the mirror, it's invisible to you because it's really smooth. But if you shine the light and then you go to the far field, that appears as an image. So just to tell you that this is, for example, I want to create this GG logo. And essentially what you need to create is creating about, let's say, 6 micron variation over centimeters. If you do that, which is extremely gentle variation, then you will create a pattern, which this pattern essentially is look like that. Of course, it may sound like very sharp, but remember that over a millimeter, or a couple of millimeters dimension, then when you look at this, you don't see any changes. And essentially, when you shine the light on the top of that, you will create an image in a volume. And we translated this in also in the liquid crystal technology. We created a flat window, essentially, which the refractive indices, they are depending on the location, they are depending on the X and Y. And with the controlling of the refractive index, we were able to create this kind of, let's say, pattern. And essentially, this is an experimental result. If you go far, just very close to the, let's say, these magic plates, you don't see any phase variation or any images. As soon as you go to the far field, you will see that the image is start to appear. And for these are for different, let's say, logos, and you will see that essentially it works for any images. Well, and being in the field of singular optics, I always am interested in finding the singularities. So what's happening with the phase singularities there? And essentially, you can probe them upon the propagation. And what you will see an extremely rich topology that appears for the point of singularity upon propagation. So I was happy. This was just only the curiosity point. So we say, well, did we understand the magic mirror concept that, say, Michael Berry proposed? And if that works in reality, or maybe there is some approximation, which essentially it's come out to be a true one. And then, of course, we try to link it to the singular optics. And for the next project, we are trying to create entangled magic images.
Can I ask you a question?
Yes, sure.
Entangled stuff. I'm just curious. It's beautiful just as an example, and the point that it works in far field so that it's not limited to one plane is interesting. I'm just wondering if it also lets you get around any limitations of standard imaging. Can you make sharp patterns that persist further than the Rayleigh range would naively make you expect?
Very likely, yes. My answer will be yes. But that depends really how much you want to have the edges to be clarified. Let's say the jumps that you want to clarify. I would say that those images in a certain planes, they are really, really sharp. But as soon as you are far away, you will see that it gets blurred, not destroyed. But before that, also you have the image. Yeah, yeah. Good point. So I wanted to, that so far was only about, let's say, the phase, right, and intensity. Now I want to tell you what is happening with the polarization. I'm sure that you are familiar with the polarization of lights, and what we do usually we map it on a Poincare sphere. The similar things that happens with spin 1/2 that you have it on a Bloch sphere. But I want to tell you that there is another concept that we usually introduce is a point of singularity, but for polarization degrees of freedom. And this singularity is not a zero in the field, is not look like a phase. So it's a mathematical singularity that we define. So when you deal with polarization singularities, of course, you can map it on a Poincare sphere, but then in general, what you are dealing with the polarization ellipse. And this polarization ellipse, for 2 different cases, will be singular. One, when the ellipse becomes C-polarization. Then I have no idea about major and minor axis. So this is what I call it singularity, and I call it C points. essentially S1 and S2, which are the Stokes parameters, they will be 0 for CQI polarizations. The other regime, which I have interest in, and I call it again singularity, is a linear polarization. The singularity happens, or let's say the ambiguity happens about the orientation of the electric field. We don't know when this is happening. If you pay attention, in this case, I don't have arrows because in both sides, upon the time it's oscillating. And then S3 Stokes parameter will be 0. I call them singularities, mathematical definition. So is S1, S2 is 0, I call it C point. When S3 is equal to 0, I call it linear polarization singularity. So I can create a very rich topological charges. I'm not showing you the intensity because now my interest is only polarization degrees of freedom. And I'm asking you what is happening here is a C point. Essentially here is CQI polarization. So S1 and S2, they are 0. And here on this line, you will see linear polarization. And essentially S3 is equal to 0. So, and if I let the beam to be propagating, I will ask you what is happening with this topology. If you see this topology, if you follow the major axis of polarization ellipse, you will see that this major axis is changing, right? So if I start from here, if I do a full rotation, I will see that this is the major axis. If I do the full rotation, the major axis is moving like that and comes back to this way. So essentially, it's rotating by half pi. Sorry, half 2 pi. So it will be a pi. So, and if I do a full rotation, I have a 2 pi. So pi in the rotation of major axis divided by 2 pi, that will be 1/2. That's the topology that I define it. So now this is a beam that you can create it. Let them propagate, or let it propagate. What is happening with the topology? The topology will stay. The only change that happens, it starts to rotate due to, let's say, going phase that we know. But you can deal with different kind of, let's say, beams. So you can create lemon, is what people they call it, and they borrow from this differential geometry. You can create the star topology. You can create the non-star topology, which is, again, I'm saying that the people, they borrow it from the differential geometry. And here, the topological charge that I described to you is plus 1/2. Here is minus 1/2. If I do rotation around a positive angle, then you will see that the rotation happens in opposite way. That's the reason that you will have a negative sign for the topology. And one question that I had, and it took us about 7 years to figure out what is happening when you take this light, this kind of topology, and you do tight focusing. And when you do tight focusing, you are not in the paraxial regime, because the paraxial regime means that the electric field is in the transverse plane, and the light is propagating in this way. But if you do tight focusing, what is happening, the wavefront will be tilted. So the electric field has a component along the propagation direction, because that will what happened with the K vector. Then, depending on the kind of tight focusing, you may get a Z component of the electric field, which will be excited further and further and further. So, for example, in this case, which the numerical aperture of a microscope is about 0.9, which is what I call it the tight focusing regime. And then if you take one of those topology, for example, the star topology, what is happening at the focus? And then that was a brilliant idea that Gerlach and Peter Banzer in Germany, they had and developed, and they could look at the EX, EY, EZ of the electric field, all three components, and looking at the relative phases between them. And this is what we got. So essentially, in theory, I'm expecting that intensity is not anymore a cylindrical symmetry. It has a threefold symmetry due to the polarization topology that you have. And now what you have EX, you have EY and EZ, but if you look at the outside, you can reconstruct also the phase, relative phase between them. This was a technique that they had the nanoparticle moving around, and they look at the back scattering and forward scattering, and from this, they were able to reconstruct the field there. The interesting point is that look at the EZ component. If you look at the EZ component, the value is about 0.2, which is, well, it's close to this range. So essentially, the Z component of the electric field is also getting excited. So you are in totally non-paraxial regime. So I can put the EX, EY, and EZ together with the relative phases, and I can look at the polarization ellipse again. And my question was, what is happening with the polarization ellipse? And surprisingly, what you will see that polarization ellipse still is in ellipse. So you are not violating, you are not going to a three-dimensional way, but probably this ellipse is tilted in space and having a certain topological structure. And if you plot the major axis of polarization ellipse, essentially what you will get a Mobius. So going from paraxial regime to non-paraxial regime, manipulating the polarization degrees of freedom allows you to get the three-dimensional topologies. So when we worked on this, and one of my students asked me, can we do in the paraxial regime, not doing the inside focusing regime, can we create some sort of topological charges or topologies for light in the non-paraxial regime? And that was the reason that we got interested in knot topology, which was first discussed by Mark Dennis and Michael Berry, and later on by Mark Dennis and Morris Paget. So here, I'm not working about this is singular optics, but again, I'm dealing with polarization, which is new. So I can create this topological structure for polarization. So certain points I have a lemon, certain points I have a star, and then I have C points, essentially C points with a negative +1 topology or -1 topology, and I let them the beam to be propagating in space, in three-dimensional space. It's not non-paraxial, it's a paraxial regime. If I engineer it properly, what is happening, then essentially I will get out, by the way, those are the points for the lemon, which is the blue one, and the red one is the star topology. So essentially they have a +1 topology and -1 topology. So if you let them propagate, what you will see, and following all of those points here, you will see a knot topology that appears in a three-dimensional way. Well, that was fantastic, and of course, it started with only a theory and you know, a curiosity. But later on, also, I was asked by the way, you can look at the cipher surface, which is the minimal surface between these knots. You can characterize the knot in a different way. I don't want to talk about this. So, and later on, when I was in a conference, one of my friends, Aisha Karimi and Eliyahu Cohen, they asked me a question. They say, well, can you give a frame to knots? Because of course, knot is a string, but it's not Mobius, right? Because the Mobius is you can have a frame on it, you have a surface. Can you give a frame to the knot? And we say, why not? We can always try to look at the major axis of polarization ellipse just nearby. And if you do that, essentially you give a frame to the knot, and essentially what you will have, you will get a new kind of topology, which is moving from a string to a surface, but this surface also has a twist inside. So if you look at the surface, you will see that it looks like a Mobius has many or certain type of twist upon propagation. And well, we were able to create this, and also we use this twist to send information in our RSA protocol kind. So what we have to say, we say, well, we want to send prime numbers, and what you can do, you can assign it to a certain braid with certain twists, and we know how to move from the braid points to the knot topology, and we can use it as a backdoor to send information. So we created this and we send it to the other side, and only by showing the knot and also the alpha and beta, which are the two arbitrary parameters, we were able to create a way that they can use knot topology to perform some sort of classical communication. I wouldn't say that is an NMP problem. Is look at RSA protocol, but exponentially difficult to be resolved. So recently also we translated these to a two-way communication, which essentially also Bob can, after the measurements, can create another knot and entangling it and sending back to Alice, and that will be two-way communication. So far, we learned about the, let's say, intensity, we learned about the phase that we can modify, we can learn about a polarization topology that we can modify. What about the frequency? Here's another way. So, well, if you deal with a certain frequency of omega, then you have EX, EY, and then in general, you have a polarization ellipse. What is happening when you have two beams, and the two beams, one of them has a frequency of omega with right-handed, and the other one has a frequency of 2 omega with left-handed. Well, people then say that they will not interfere. Well, you have to be in ultra-second regime or ultra-fast, and you will see that the tip of electric field, because electric field follows the superposition principle. So if you look at the tip of electric field, what you will see, the tip of electric field is moving in a certain topology, which is not an ellipse, because that was for monochromatic one. It's something like a Lissajous pattern, if you remember. It looks like two harmonics, essentially, two orthogonal harmonics. So, and of course, what you can do, you can also go beyond these. You can go with frequency of omega, 2 omega, and 3 omega with different polarizations. And what you will get now, you will get a knot that for the tip of electric field is different from singularities. Now the tip of electric field upon the time is moving on a three-dimensional topology. You can do the tight focusing, and what you will get a zoo of knots. So you will get extremely rich topology, which point by point, you have different kind of knots. You can analyze them. You have a trefoil, figure-8 knot, synchrofoil knot, or a half link, or any other topologies that you want. So that's really interesting, and I'm very much looking forward to see an experiment that people they can look at geometric phase of these kind of beam interacting with the material, which allows you to see beyond the two-dimensional geometric phases. Well, being in Ottawa and next to Paul Corcom, you have the interest to look into creating these kind of beams, but in a high harmony at different wavelengths. So one way that we were able to do, which essentially was a beautiful work of Paul Corcom's team, was interacting these let's say structural light with noble gases. And then what you will get due to the conservation law, you can transfer certain orbital momentum to high harmonic generation. So essentially you will get a beam which is having odd frequencies. So you have 3 omega or 5 omega or 7 omega or 17 omega going to let's say 10 or 15 nanometer wavelength, but all of them, they are structures. So we can just simply transfer what we are creating in the fundamental into the high harmonic regime. And if you look at the perspective of this, you will see that it happens in the atomic level. So this quantization, or let's say this conservation law, applies also to orbital momentum degrees of freedom or to spin degrees of freedom. So we were also able to shape high harmonic generation, the polarization, and also orbital momentum of high harmonic generation. And also you can create, for example, an azimuthal electric field, which when you're applying to a material, then you will create an azimuthal current. And these azimuthal currents may give you about few Tesla of magnetic field, which is amazing. So with this, I will conclude the structural light, and I will go now to quantum communication, quantum information theory. So why I care about structuring photons? Well, in the first slide, it was clear that, well, L will give me a Hilbert space, which is unbounded. P also gives me a Hilbert space, which is unbounded. And statistic also will give me, which people, they work on these. So they work with, for example, coherent state or squeeze state. You can work with the polarization. This is what people in quantum communication, they deal with. They work with the qubit, and essentially you are only manipulating the polarization degrees of freedom. Or you can work also with omega, which what people, they work with multiplexing, wavelength multiplexing. So assuming that you have, you can fix all of them, right? But only working with orbital momentum degrees of freedom. So essentially, this is one of the examples. So I can go with L equal to +3 to L equal to -3, including the 0, I have a 7-dimensional space. So I can go also create a discrete Fourier transform of them. This is what you needed for BB84 protocol, standard way, but high-dimensional way. And then you can look at the information that you can send it. And these, after privacy amplification, then you have a QBER, which is the quantum bit error rate. And according to the error that you do have in your system, you defines that you have a positive key shared between Alice and Bob or not. So for example, in the standard BB84 protocol, after the privacy amplification, if you have 11% of error, you don't have a positive key. Essentially, you have 0 positive key. If you say I have 5% of error, I'm in this regime, then I have about, let's say, half beat perceived photons between Alice and Bob shared. If you go to higher dimension, what is happening? Even if you have, let's say, 11% error, if I go to the dimension 32, essentially I have about almost 5 bits of information perceived photon. So this allows you, by going to that higher dimension, allows you to even work in a regime which the noise is high, but still you can send more information more securely than the conventional way that people they are thinking about. Well, of course, you can build up, let's say, a quantum simulator if you have access to high dimensional space. And you can go, for example, to simulate two-dimensional material system, to go to the cycling system, or even right now we are thinking about going to a torus, for example, combining two cyclic system together, and then you can simulate a material which is look like a torus or even nanotube, carbon nanotube. So how can we create them in a laboratory? How can we create a high dimensional entangled state? Well, we use bulk optics. So essentially, we take a photon, UV photon, and eliminating a BBO crystal, which is a nonlinear crystal, essentially. And then, due to the conservation of linear momentum and energy, what you will get correlated photon pairs. And when you create the photon pairs, then now you can look at them, what is happening with the correlation between biphotons. If it's a polarization degrees of freedom that they are getting entangled, or is a special mode that they are getting entangled, and etc. So I'm explicitly talking about type 1 because I'm having interest in high dimensional topologies and high dimensional spatial mode. And essentially, Anton Zeilinger was, I think, the first person that showed that orbital momentum is conserved. So if you pump it with a Gaussian pump, which is Gaussian UV light, then you will get the correlation between orbital momentum degrees of freedom. So signal on either photon, the sum of the orbital momentum will be 0. If that one is -1, the other one is +1, and then I don't know which one is which, then you will get entangled state. Okay, and +2, -2, and etc. So if you shape the pump such a way that the pump has orbital momentum of +1 or -1, then this symmetry is broken. So then you will get the correlation between +2 and -1, and vice versa. You will get +3 and -2. So that's a beautiful way to show that, well, this nonlinear process also, the conservation happens in orbital momentum degrees of freedom. And we were curious what is happening with the P degrees of freedom. So because also P is important. So P dictates what is happening with the radial parity. And in that beautiful experiment, which was really time consuming, Alicia showed that in the SPD process also, the radial parity will conserve. So in addition to L correlation, you have a correlation in P degrees of freedom. So since this was extremely difficult, we had a visitor from Fabio Sciarino's team. We tried to develop a digital holography on biphotons. So essentially having two cameras, which they are 256 by 256, look like APDs. You can look at the correlation between each pixel within 2.5 nanoseconds, and having a reference beam essentially allows us to look at the correlation between any modes that you want in a fraction of seconds. So essentially within, let's say, 1 second, we could conclude what is going on with the correlation, not waiting, let's say, several weeks to do the quantum state tomography. And those are, for example, one of the correlation. If you go with the Gaussian pump, you will see the correlation in L or in P. And if you go with, for example, with orbital momentum of, let's say, I think that's a +1, you will get this correlation. If you go with superposition, you will get this kind of correlation. And finally, if you go with something which is correlation between different P values, you will get extremely rich, let's say, correlation between P and L's. And of course, we have interest to use them for high dimensional quantum key distribution. We send it, let's say, we had Aris and Bob, and essentially connected by a classical channel. And then we decided to go with different protocols and verifying when high dimensional space will be useful and also overcome some limits that we have in bidimensional cases. And we changed, for example, the protocol of Char 15, BB84, tomographic way, and also Singapore protocol. And we went for dimension 4 to dimension 8 or dimension 2 to 8, and etc. And we had what we are expecting in terms of experiment and in terms of theory. And at the end, we look at the key rates, essentially, which is given by the rate that we can modify it, and looking at the sifting protocol as well. And finally, having an established, let's say, key. And turned out that, well, I'm in favor of high dimensional, but due to the imperfection in the laboratory and also problems and challenges that I have in the laboratory, only dimension 4 is the best one with the current detector, current SLMs, and etc. And that was fully automatic, by the way, and no human interface. We let the two computers involved make a decision which protocol they have to go for and what they have to choose. And at the end, they will calculate the error rates. And it turned out that only dimension 4, with the detectors that we had at the time, and we did the generation and detection scheme, was the best. Right now, we have a new setup, which is dimension 16 is the best one. So with this also, I want to tell you, you can also look at the fundamental way and see if whether the high dimensional also will give you a benefit. And one of these way is looking at the optimal cloning attack to a channel. So essentially, you can have a communication channel. Of course, we have no cloning theorem, but you can ask yourself, what are the best way that I can make as good as the original copy? So you can attempt to attack to the channel and getting some kind of information there. And we realize is that if you go to higher dimension, this attack is more easy to be revealed. So the error that you introduce due to the attack is way higher than the two-dimensional cases. And essentially, I can give you that it shows as a kind of fidelity. If you go to higher dimension, the fidelity of the cloning will be 1 divided by 2 plus 1 divided by d plus 1. So going to higher dimension brings the fidelity lower and lower and lower. It means that you have more errors in the channel. So that was another way which we again we automatize setup, and we look for different attacks, intercept percent, and also optimal cloning attack, and we look at the process matrix of a channel, and we find out, well, going to higher dimensions is way easier to reveal the existence of eavesdropper. Fantastic. And we students, they like to go outside, sometimes having roof party. So they went to the two different groups at the University of Ottawa, and they try to send single photons, but going to the dimension 4. Instead of sending 0, 1, they send 0, 0, 0, 1, 1, 0, and 1, 1 bit, going to the 4-dimensional space, because we knew that is good, is better for our schemes, and try to send also with entangled pair. They work with entanglement. And finally, they were able to show that, well, you can go from 2-dimensional space to 4-dimensional space, and what you will get as a benefit. So in one night, for example, we had about 11% error, if you look at here. So for 2-dimensional, we had about 0.43 bits per, 0.5% error, and we had corresponding one, which was 0.43 bits per sifted photon. And of course, this error came from the building vibration, the turbulence, many other issues. So it was time dependent. And in a certain time, we had about 11% error, which we couldn't use the 2-dimensional one. So we changed the protocol to 4-dimensional, and still we get a bit rate, which was higher than the 2-dimensional in the best scenario. So that was a good one. And right now we have a free space link between the University of Ottawa and NRC, which is 5.4 kilometers. Should I say, it will be recorded, and just for 2 years it was down, the link. And a couple of weeks ago, politicians, they came, they want to see the link, and I realized that the window was broken due to the storm, and pigeons, they went inside, and it's terrible. So I had to spend thousands on just cleaning those the link, essentially. And we do have scintillometry, which essentially we can monitor the turbulence, because the turbulence is the main factor for the free space communication, classical and quantum. And why we choose 5.4 kilometers, because is the turbulence, amount of turbulence that you will see on the horizon is identical to amount of the turbulence that you will see from the ground station to a satellite. So we can essentially simulate the turbulence perfectly there. And we have adaptive optics system with a supercomputer, which quickly can adapt and see what is the turbulence, and also with the adaptive optics system, you can eliminate the turbulence there. So with these also, I would say that they didn't only like the roof party, but also they liked the pool party. So they decided to bring equipment to a swimming pool first. And you see, of course, Alice is trying to do communication with Bob, which is Azad. And you know who is doing the main work is Felix, which is in the swimming pool and trying to align the optics. And it was a classical channel which was going on the ladder. And we have a quantum channel which was under the water. So they were sending information through the water. Of course, we have to monitor the turbulence there as well. And we realized that the turbulence is way different from the free space. It's extremely stronger. And we try also, they decided to have a barbecue in a cottage in the Ottawa River. I don't say to insect people. Then they spent 2 weeks there, and they try to send information in a real field. Essentially, when you have algae, you have particles in the air, in the water. So we were not able to go more than 6 meters there because we were extremely unlucky. We received a couple of rains at that period, which essentially destroys the condition that we expected. And yes. People, they say is a submarine application. So essentially, you have a $100 million facility underwater, and they want to do communication. What is the communication that they do is acoustic mainly. So even from North American coast, we can listen to Russian submarines. Yeah, that's the argument. For myself, no, there are many sensors underwater, and you want to extract the information from them. And one way that people they do right now is sending someone down and take the sensor off and replacing a new one, which is not cost effective. Okay, so you can go with optical domain, even is a kilobit per second, still you can extract the information that you want with minimum amount of, let's say, money, I would say. And then, and of course, multiplexing is extremely important, which is going to higher dimension because you can send more information at the same time. What we realized that, well, going to the dimension 4 is extremely difficult because we need to have a compensation for the turbulence. Below that, yes, we can do. And the very recent one, just during the pandemic or at the beginning of pandemic, was going to NRC and having a flume and having a trail which you can essentially control the distance. And you can look at the distance that you can send the information in polarization and also in the vector vortex mode on orbit and millimeter degrees of freedom. And it's a setup that is not really look like the laboratory, quantum optics laboratory is very fun one, I would say. So you should follow the protocols going inside, which is safety protocols, of course. And yes, and then for just to tell you why water is very different environment, Alicia is sending 2 very bright blue and green laser. And I asked her to do that intentionally because we want to see what is going on with the scattering and absorption in water. And you will see that mainly after the distance is blue. Why? Because that's the transparent window, which I escaped one slide about that. That's really a limited window for water that you can allow. It allows you to do optical communication in water. Okay. And the maximum distance that you can go based on Beer's law is about 200 meters. But even 20 meters is sufficient to do, let's say, communication between submarine and a plane or drone or satellite. And we were able to reach to the distance of almost 30 meters, which was a record. And still, we were able to send about 80 kilobits per second, which is really, really high. Okay. Oh, yes. Yes, excellent question. So essentially, you can go with the attenuated coherent state, or you can go with SPDC. Of course, it's very, very unlikely that you can get a UV light SPDC there. We were able to get it close to green for some of the experiment. For some of the other experiment was just simply attenuated laser beam. I hope that I answered to your question. What time is it? Just having.
5 or 6 minutes.
Oh, 5 or 6 minutes. Ah, that's easy. I had so many materials to show. So now I briefly discuss about structured matter wave, which is electrons. So we, with a very nice theoretical work of one of my colleagues, Konstantin Bliok, in 2007, we realized that whatever we do with photons, you can also translate it to massive particle. Essentially, what you deal is a wave function. As I showed to you in the beginning, also I can have a wave function for a photon. And on the other side, well, the equation that you have it for matter wave is a relativistic one, is a Dirac equation, or you can go with non-relativistic regime, which is a Schrödinger equation. I assume that there is no potential, it's a free particle moving around, okay? If you do a little bit of mathematics, which is extremely simple, what you will see that this can be translated into a Schrödinger equation like or partial wave equation, if we assume that you have a certain P vector or P momentum and certain energy for the particle. And if you assume this, then you will get to a Schrodinger, partial wave-like approximation, which is exactly describing that you can have the same wave function for massive particles. What you had for photons can be done also with electrons. And this is one of the examples. You can get the transverse mode, which is okay. So you will get the transverse mode, which is essentially is given again with the same quantization, which is L and P. And also you have a longitudinal one, which is given by what I call a longitudinal index, which tells you that you are dealing with a matter wave, which essentially in the space-time is look like this, within the first approximation, by the way. So it's a Gaussian in along Z, but also it carries a certain phase or let's say probability distribution. Now I am careful. I'm using the probability distribution and others. But what is happening more? Photon doesn't have a charge, right? Doesn't have electric charge. But electron, if you want to, let's say, create structured electron beams, then electron has an electric charge. Then what is happening with the electric charge? Essentially, you can do the calculation to find what's going on with the current density, and essentially you will deal out with an azimuthal current, which this azimuthal current will give you a magnetic moment for these structured electrons. It looks like that you have an electron. It looks like an atom. They're taking the nucleus out, but the electron is propagating and having an orbital angular momentum. And well, our electron is not rotating; is a wave function. If I can plot it to you what is happening if you go with the classical regime. But essentially, what you are creating a magnetic moment due to the azimuthal current that you have. And this magnetic moment is quantized. It's given by L mu B, which is just given here in the lower part. And the L factor that you have is showing to you that is unbounded. It's not look like the spin. So spin is bounded by plus and minus 1/2. And here is L mu B. And people that they work in electron microscopy, they appreciate this because we don't have a spin polarized electron microscope. We don't have it in the middle energy range. So this is another way that people they can create a magnetic moment for the electrons, and you can use them in electron microscopy. So that was the first, it was done by Yoshida in 2010. Then it was done by Joe Verbeck in the holographic approach, which you can control the phase of the electron beams. And finally, you can, due to the diffraction or due to the interference, you will get an electron beam, single electron, which carries orbital momentum. Or you can do it with the electric field, or you can do it with a more sophisticated holographic approach, which I think it took us about 2 years to approach this range. So essentially, if you have a single electron in electron microscope going into a hologram, you will see the diffraction orders, and you will see in the first order of diffraction, you have an electron which is twisted or having certain orbital angular momentum or certain magnetic moments. So I will try to be quick. Why this is important? Because essentially you can create any electron wave function that you want with any approaches that you can do. So you can create, for example, a hologram, a really complicated hologram, which shapes both the amplitude and phase of the electron. And essentially there's a result that you will have it here. It has a certain P value and certain also L value. And this is the shape of the hologram essentially that you will see. We are talking about 20 nanometer dimension. This is a 3D version of making a nice, let's say, movie of that what is it look like in reality. So the total dimension that you have is about, let's say, less than 5 micrometers, but you have to craft it with electron beams. And then you can create the highest topological charges that you can do. For example, L equal to 1,000. Orbital momentum. So essentially you have 1,000 mu B magnetic moment. And also you can, for example, create an AD beam, the same scenario that Ebrahim, one of my good colleagues in Tel Aviv, he did. You can create Bessel beams for electrons because then the Bessel beams, you know that it has this property that is not changing. It's not depending on the plane wave. Essentially, is the same shape, shape invariant. And then you can also create a sorter, which essentially you can extract the information after the interaction with the sample. So essentially, you have a sample which you have absolutely no idea what's going on with the sample, but then after the mode sorter, you will understand what are the magnetic property of the material by doing the proper post selections. Essentially, that was a magnetic dipole laid on in the transverse field, and then we interacted an electron with it, and then we had a sorter which was decomposing in different orbital momentum values, and finally we were able to create and reconstruct the value of orbital momentum due to this interaction. And from this, we were able to reconstruct the magnetic field, which essentially here you had about almost 1 Tesla, and around this you had about millitesla. So, and this is the illustration of how this system works in a real electron microscope. Essentially, you go from one plane, you have an electrostatic version of that, which right now we just filled the patent. Essentially, that electrostatic interaction will give you a dynamical phase, which you can shape the electron, and finally you can sort them in a certain basis. So there are different ways. Also, you can look at different approaches that you can shape the electrons, either with a magnetic field or with electric field. Both of them, they are geometric phase or varied phases, but one of them is a two form, the other one is a one form. Essentially, if you deal with the electric field, essentially you're dealing with the first approaches, while if you go with the magnetic field, you are dealing with the two form. And we explore both regimes essentially by applying only electric field between two plates, and the electric field when it's changing from -10 volt to +10 volt, you can create an electron vortex beam, which is the topological charges is almost about, let's say, 20 to -20. So with simple controlling the voltage, you will be able to create electron beams with a certain topological charges. And I will not talk about this. Sorry, is very complicated because that's solving a very important puzzle in electron microscopy, which is a spin polarized electron microscope. You know about Schrödinger law, right? So Schrödinger law does not work for electron. It works for the atoms or ions. When you try with a single electron, it does not work. And the precision that you should have is about the wavelength of the electron, which is a picometer. So which is a puzzle, and Bohr and Pauli, they had a discussion about that. Well, the spin doesn't make sense for free electron, or it should be bounded electron. So I will encourage you to read about that. It's a very interesting puzzle. And what we propose instead, we say, well, I know how to work with orbital momentum, how to sort it, but I can create a device that couples spin to orbital momentum. Now, instead of sorting spin, I can sort orbital momentum, and then I can filter out the scenario. And of course, you can look at the time probe, which essentially today during the visit I mentioned. You can have an electron microscope, which you can create electrons in a pulse way, and then you can illuminate the sample, and you can do palm probe experiment, and essentially you can create electron vortex beam with really high topological charge. With a really fast way to control the topological charge, essentially in attosecond way of controlling the electron topological charge. And with this, and this, I will stop here. Okay, so well, we are interested in fundamental studies, building up the first quantum electron microscope in Canada, hopefully next year, if it will get funded. And then helping with the Quantum Internet Canada, which with some of colleagues, we are in a team and we are trying to develop that. And of course, I should say that, well, this is a work of many, many people, including members of my team, which I learned so many different things from them. And each day I'm learning from them. And many, many great scientists all around the world, which they helped me to learn this process. So my apologies, I went 3 minutes more.